All right, welcome back to another calculus lecture. So in today's lecture, what I want to do is give the formal definition of the definite integral, sort of in the same way that I gave the formal definition of the derivative a long time ago. So just like that, with the formal definition of the derivative, we're going to come up with some rules later on that allow us to not have to use this definition every time we want to compute with the integral, but just so we understand the integral, we're going to spend some time going through it today. In order to do that, we're going to need some notation and some definitions that will make things a little bit easier. So before we get to the definite integral, let's maybe recall something we did last time. So recall last time we looked at expressions of the form, and we had things like, 2 times 20 plus 3 times 30 plus, or 2 here plus 2 times 40 plus ... And we had a lot of things we were sort of summing up. When we did the velocity question, when we had velocity data every second, it got a little bit messy to sort of write that every time. So in order to make this a little bit more friendly to work with, because we need to deal with these expressions a fair bit for the definite integral, we're going to introduce some notation. So notation. This is summation notation. So basically, the notation and here I'm going to write it as j goes from a to b of f of j. So the way that we read this is j, the sum as j goes from a to b of f of j. So all this means is I'm going to start at the value a, and then I'm going to add up all of the successive sort of functions evaluated as I increase this index by 1. So I'll have f of a plus 1 plus f of a plus 2, so on and so forth, up to the upper limit of summation, which is b here. So all this means, this notation just means I'm going to take and I'm going to add a bunch of things at different indices, like this. So the notation is read, I'll reiterate this, the sum as j, and we could use any variable for our index here. I might use an n sometimes, or an m, or a k, or an l, or something like that. It doesn't really matter. The sum as the variable j, the sum as j goes from a to b of the function f of j. Okay? So this notation is just a succinct way of writing just a sum of a bunch of things like this. It makes writing these things a lot less sort of cumbersome. Okay, so with this notation, I want to also give a another definition which is going to be used when we define the definite integral. So definition. And these are going to be left and right-hand sums. So let f of x be a function and a to b an interval and then we're going to let n be a positive integer. Okay, so I've got some function it's going to be defined on some interval, a to b, and then I'm going to have in just some number. You can think of it as 5 or 100 or 1,000 or whatever you want. So the left hand sum L sub n is defined as, and I'm going to write it like this. So maybe L of n is equal to the sum as j goes from 0 to n minus 1. Notice there are n things in here. If you count from 0 and you go up to n minus 1, you have n number of things because you started at 0 and not 1. So what we're going to do is we're going to take the interval a to b, and we're going to divide it into n subintervals of equal width. And the width of each of those subintervals is going to be the width of the total interval divided by how many intervals I chopped it into. Okay, so this is the width of a subinterval of a to b, and then I'm going to multiply this by the function evaluated at the left endpoint of each of these intervals. So I start with the leftmost endpoint, which is a, and then I add on some multiple of this width. So j times b minus a over n. And what this is doing is this is just picking out all the left endpoints of each of the n subintervals that I've divided my total interval into. Likewise, and I'll draw a picture here in a moment of what this represents. We've already sort of seen it before. The right-hand sum R sub n is defined as R of n is equal to, and now I want to do the same exact thing, except that what I'm going to do is I'm going to evaluate my function at the right endpoint of each of my subintervals rather than the left endpoint. Well, the right and left endpoints agree on or overlap on a lot of these intervals, so really all that changes is just how you index this sum. So instead of going from j0 to n minus 1, you're just going to go from j from 1 up to n. So we're just going to shift it by 1. And again, we have the width of each of the subintervals times the function evaluated at the right endpoint. Okay, so again, width of a subinterval right endpoints of the subintervals. Okay, so maybe let's go ahead and draw a picture and think about what does this quantity actually represent. Well, we've sort of already seen it before in the last lecture. It represents one of these approximations to the area underneath the curve. So I should get purple out. Example. So if my function looks something like this, this is f of x, and then this is the interval maybe 0 to 2, and this is 1. And if I wanted to do the right endpoint approximation with maybe, I don't know, 4 subintervals, so let's do r sub 4 for, whoops, using the wrong color here. I want to draw something with pink. R sub 4 for f of x is the sum as j goes from 1 to n, well actually not up to n, up to 4, of now I have I should say on 0 to 2. The width of my interval here is 2, and I'm going to divide that by the number of subintervals I'm making, which is 4. And then I'm going to do f of the left endpoint, 0, plus one of these, one of the widths of, or some multiple of the width of each subinterval. So j, and then 2/4 is just 1/2. Well, maybe we'll just write 2/4 just to be clear. Okay, so this is what it is, and then geometrically, it represents the following. So each of the subinterval marks is going to be at the 1/2 mark, and I start with 0 plus 1/2, which is just 1/2. And then when j is 2, I'm at 1. When j is 3, I'm at 3/2. And when j is 4, I'm at 2. And I'm evaluating the function at the right endpoint of each of these subintervals. And so what I end up with is something that looks like this. Not the most perfect drawing, but you get the point. So notice what this is computing. It's computing the area of these rectangles. I'm taking the width of each of the rectangles, the width of my subinterval, and I'm multiplying it by the height of the rectangle. That is where the function is being evaluated at the right endpoint here. Okay? So all a left or right hand sum represents is it's just a succinct way of communicating the geometric meaning of the area of all these rectangles added together. Okay, so I know the notation can look a little bit daunting. Holy crap, my hands have a lot of ink on them. But the notation can look a little bit daunting, but really all it's communicating is just this simple sort of geometric idea of adding up areas of rectangles. So width times height, and then add them all up. Okay, so nothing too mysterious there. So we've got this notion of left and right hand sums, and at this point we are ready to define the definite integral. So we'll get some blue out here. So definition, the definite integral. So for a function defined on a to b, and we should say a little bit more about what kinds of functions can be defined on these intervals. You can sort of think about, well, it's possible to construct really sort of crazy and wonky functions, so we should put some restrictions on these, but for the moment, let's not think about that. We'll think about functions that are sort of nice enough and that come up in usual applications that we would be familiar with. So for a function defined on a to b, the integral of f of x over a to b is defined as, and the way that we're going to write this is this little sort of scripty s for an integral sign, f of x, and then we need to indicate the variable that we're integrating with respect to, so dx, this, and then from a to b. What this notation means is that we're actually going to take a limit as n goes to infinity of r of n, or the limit as n goes to infinity of L of n. And it actually doesn't matter which one we choose. So we could take the limit as n goes to infinity of R of n, or the limit as n goes to infinity of L of n, and these two things will actually be the same. They will agree. So remember last time we sort of looked at, if I had a more and more accurate velocity measurement, I was able to get a better approximation of the area under the curve. Well, we can get the exact area under the curve by taking sort of infinitely many subintervals here. This is that limiting process. As your accuracy gets better and better and you take more and more subintervals, this quantity, these left and right sums, those approximations that we had to the area under the curve, those converge to the integral. And the integral represents the area under the curve, or at least the area between the curve and the x-axis. Kind of as before, we had sort of net distance traveled and things like that. The integral is going to represent that. Okay? So this is how we're going to define the definite integral, and we're going to have some rules in the next lecture that show how do you actually, compute this without having to do a limit computation every time. We will see how to do that, but actually for the moment I do want to do one example computation where we compute an actual integral using this limit definition. So example, compute the integral from 0 to 2 of x dx. Actually, we're going to do 0 to 4 of x dx. So my function here is just the function x using the definition of the integral. Okay, so we need a left or right-hand sum. For convenience, we'll just do a right-handed sum. So r sub n, in this case, is going to be equal to, well, the sum. We just write down what the definition of a right-hand sum is. It is the sum as j goes from 1 to n. J is going to be my index here. I have the width of a subinterval. The total width of this interval is 4 minus 0 over 2. I'm sorry, not over 2, over n. So I have total width of 4, and I'm dividing it into n subintervals. Each one of them is going to have width 4 divided by n. And then I take my function, f, I evaluate it at the left endpoint plus some multiple of the width of each of my subintervals. So j times 4 minus 0 over n. And this will be equal to the sum as j goes from 1 to n of 4 over n times, now we can actually just put in what f is. It's just x, so I just write down what this is. I have j times 4 over n. Okay, and this simplifies. So notice the 4 over n doesn't change with respect to the variable j, and I have that in two places, so actually this is 16 over n squared times the sum as j goes from 1 to n of j. Okay, well, I need to actually compute what this sum is, and there is actually a formula for this sum. So this is going to be equal to, and this, if ever I give you a problem like this, I'll give you the formula that you will need to compute this sort of sum. So this is 16 over n squared, and the formula for this is n times n plus 1 over 2. So you take the top limit of summation, you add 1 to it, and then you divide by 2. And you have to start at 1, so that's why we did a right-hand sum here. And when we simplify this, this is equal to 16 over n squared times n squared plus n, so I just distributed this n to each of these over 2. And this is going to be equal to 8 n squared plus n divided by n squared. Okay? Now, what we need to do is actually take the limit as n goes to infinity. So the integral from 0 to 4 of x dx is equal to the limit as n goes to infinity of r sub n. So I'm taking smaller and smaller subintervals. I'm getting a more and more accurate estimate. This is equal to the limit as n goes to infinity of 8 times n squared plus n over n squared. And if you remember way back, we had a method for evaluating limits of rational functions like this. So here, my power of n is the same in the numerator and the denominator. So as n goes to infinity, all I get is just the ratio of the leading coefficient. So this is just going to be 8 divided by 1, which is 8. And I have computed my integral using the definition. Now, if we wanted to check ourselves, we note that the function x simply has the following graph. Okay. So if I wanted to graph this on the Cartesian plane, then it's just a 45-degree line emanating from the origin. So I can compute the integral by remembering that the integral represents the area between the curve and the x-axis between the interval, or on the interval 0 to 4. So it just represents this area. Well, the area is precisely just the area of a triangle. It's 1/2 the base times the height. Well, this is 4 times 4 is 16, divided by 2 is 8. And so we see that this process really does capture the actual behavior of the function in the area underneath it. Okay? So there's another sort of thing that we can do. If I give you an integral, I can ask you to compute it using the limit definition, but just to sort of make sure that we understand what this notation means, I might give you a right-hand sum and then ask you what integral that would correspond to. So another example. So what integral does the sum, and we'll do sum as j goes from 1 to n, of 6 over n times 2 plus j times 6 over n squared. What integral does this correspond to? Okay, so I have a right-hand sum here, and I want to know if I took n to infinity, what's the integral I would actually end up with? Well, the integral sort of needs a few things. It needs an interval, and then it needs a function. So the interval here, I know that it has width equal to 6, so width of the interval is 6. Remember, to compute the right-hand sum, I do the left, or the right endpoint minus the left endpoint, which gives me the total width of the interval. So the width of the interval is 6, and then that's the sort of the width of each of the subintervals here, the 6 over n. So now this must be the function evaluated at the right endpoints of each of these intervals. Well, we know that we write this by starting at the left endpoint and then adding some multiple of the subinterval width. So this left endpoint here should be 2. And now, so the interval is, well, I start at 2, and then it has width 6. So I go up to 8, because 8 minus 2 is 6. And then lastly, I need to think about what am I doing to each of these endpoints? What's the operation being performed on them? What function am I plugging them into? Well, I'm simply squaring them. So my function should be x squared. So the integral is, I should have done this on another page, but alas. So this is the integral from 2 to 6 of x squared dx. So this right-hand sum corresponds to this integral. Okay, so this is just a way of checking to make sure that you understand what the notation means and what a right-hand sum represents, and how to figure out sort of, if I'm given an integral, what's the right-hand sum, and vice versa. Okay, because maybe I saw this sum, but I didn't know exactly how to compute it. Well, I can liken it to an integral, and maybe the integral I can evaluate by geometric methods, as we did up here. Okay, so that's everything I wanted to talk about in this lecture. In the next lecture, we will cover rules for integration so that we don't have to, or actually, we're not going to do that next lecture. We're going to do that 2 lectures from now. In the next lecture, we're going to talk about the fundamental theorem of calculus, the really big idea that sort of gives Newton the sort of place of prominence in calculus, because he's the one that sort of came up with this and was the first one to see it. Okay, and that rule is the fundamental theorem of calculus. That theorem is going to relate differentiation and integration, and really is going to be what makes everything go round. All right, so I'll see you all in the next lecture.